All right, welcome back. This is the fourth video lesson in the electrostatic series. And in this video lesson, we're going to look at some more Coulomb's law problems, but we're going to look at some two-dimensional problems. And so that two-dimensional and/or we're going to be dealing with multiple charges. So let's start out with a multiple charge problem. And so I'm going to place a few charges here on the screen. Just kind of choosing them at random here. All right, so up at the very top, that positive and negative, you can see that was just like my bank of charges. Don't even pay attention to that. These are the charges right here that we're concerned with. So we're looking at three charges that are in a row, and let's come up with some distances here. Let's say that these two are separated by a distance of 5 centimeters, and let's say these two are separated by a distance of, let's say 7 centimeters. Okay, and then let's say this one has a charge of positive 4 microcoulombs. This one is negative 3 microcoulombs. And then this one is negative 6 microcoulombs. And I'm just making this stuff up as I go, just to give us a problem here. Now, this one is a little bit different than before because now we're looking at three charges. And so it's not as simple as just saying attractive or repulsive or anything like that, because now we have three charges. And so you could get something like this on a test, and then I could ask you, find the force and direction, because we always want to find direction. Find the force and direction on, and then it'll choose a random charge. I'm going to say on Q2. So that's the one right here in the center. This one's Q1, this one's Q2, and this is Q3. So I need to find the force acting on this charge, and then what is the overall direction. Okay, now what makes this one just a little bit more difficult is the fact that you really have two forces that are going on at the same time. And so what we first need to do is we need to draw a force diagram for the charge that we are analyzing. Force diagram. Okay, we want a force diagram for Q2. All right, so right here. So let me draw my dot right here. I'll do it down here. So this dot represents Q2. What I first want to do is I want to analyze what is the attraction or repulsion or whatever. What's the force going on between these two charges? So for just a moment, ignore Q3 over here. Pretend it doesn't even exist. Just look at these two charges. What is the effect of the positive charge on Q2? So in other words, what if Q2 could feel a pull or a push in one direction or the other, what would it be? Well, positives and negatives attract to each other, right? So we could say that the positive charge is pulling Q2 to the left. Q2 feels pulled to the left because it wants to get closer to the positive charge. Okay, so this is the force of charge 1 and charge 2. So I labeled that force 1-2 because that represents the force that's being experienced between 1 and 2. Let's do the same thing over here. So now for a moment, pretend that the positive charge does not exist. It's only these two charges right here. So what's the force direction that's going to be experienced here? In other words, Q2 is going to feel pushed or pulled which direction? Well, negatives, since they're both negative, they are like charges, and so they're going to repel. And so this negative charge over here is going to want to push Q2 also to the left. So Q2 actually feels a double force in the same direction. So not only does it feel pulled or attracted to the left to go towards charge 1, but it also feels pushed to the left because it wants to get away from charge 3. And so they're both going in the same direction. And so when we think about my forces, my sum of the forces, or the total force acting on charge 2, is going to be whatever the force is experienced between 1 and 2, plus whatever the force is experienced between 2 and 3. And that's because they're both going in the same direction. If they were going in opposite directions, then it would be minus. And we'll do an example problem like that on the next slide. Okay, but that's what my sum of the forces equation is going to look like. So what I need to do is I need to do Coulomb's law twice. I need to do it once for the force between charge 1 and charge 2, and then I need to do it a second time between charge 2 and charge 3. So let's do the force between 1 and 2 first. Okay, so that is going to be found, force is going to be found by taking my k, 9 times 10 to the ninth. I'm going to leave the units out this time because you get, hopefully by now, how the units cancel. So 9 times 10 to the ninth is the k. Charge 1 is the positive, and let me scroll up here so we have it there. There we go. Oh, it scrolled back down. All right. So charge 1 is 4, and then it needs to be times 10 to the negative 6 coulombs. And then charge 2 is 3 times 10 to the negative 6th. Notice, once again, it's the absolute value. It doesn't matter because we already know what direction it's going. So the negative and the positive doesn't make a difference. And then it is separated by a distance of 0.05 meters, and then we square that. All right, so let's go ahead and calculate that real quick. Okay, so the force that's experienced between charge 1 and 2 ends up being 43.2 newtons. Okay, so I'm going to kind of squiggly that so I can remember that. All right, now let's do the exact same thing, but now we're going to look at what's the force experienced just between charge 2 and charge 3. So we're going to set it up just like before. That force is going to be equal to 9 times 10 to the ninth. Okay, the charge of Q2, remember, was 3 times 10 to the negative 6 coulombs. And then if we scroll back up, charge 3 is the negative 6 microcoulombs. And so absolute value just makes that 6, and then times 10 to the negative 6 coulombs. And then that distance is going to be 0.07 meters. And we are going to square that. And then let's go ahead and calculate that. Okay, so when you calculate that out, you should get 33.1 newtons approximately is the force between charge 2 and charge 3. So to wrap up this problem, to realize what's happening, notice what we've discovered. We've discovered that not only does charge 2 feel attracted to charge 1 with a force of 43.2 newtons, but we also know that it feels repelled to the left by charge 3 with a force of 33.1 newtons. And so since they're both facing the same direction, my sum of the forces on charge 2 is just going to be the 43.2 newtons plus the 33.1 newtons. And so that gives us a total net charge acting on charge 2 of 76.3 newtons. Finally, for the direction, it's not enough to say attractive or repulsive because now there's 3 charges. So when you have multiple charges, you need to specify the specific direction. And so what direction would it go? Well, they were both facing to the left, and so clearly it must be going to the left direction. All right, let's go ahead and do another example of a 2-dimensional problem. Okay, so now we're on our second problem, and you'll notice it's set up very similar to before. I've already actually got it set up so to save us a little bit of time. All right, so we have 3 charges that are in a row, just like before. We have 1 negative and then 2 positives. We have 3 centimeters distance between the first 2, and then 4 centimeters between the second and third charge. And the charges are listed up here. So we have charge 1 is negative 4.5 microcoulombs. Charge 2 is positive 3.1 microcoulombs. And then charge 3 is positive 2.9 microcoulombs. Now, the question wants us to find the force and the direction on Q3. So this one right here. Okay, so now we're not doing the one in the center, we're doing the one on the very end. But we're still going to do it the exact same way that we've done before. Okay, so first thing we need to do is we need to draw a force diagram for Q3 only. So there's Q3, and we need to analyze what direction does it feel pushed or pulled based on the other 2. So let's first look at the interaction between charge 1 and charge 3. And I think it's a good point to remind you that although we're dealing with static charges, meaning they're not moving, they're still going to feel forces within their proximity. So even though they're not moving, they're still going to feel an attractive force. Just like if you're on top of a mountain just standing there, you're going to feel pulled towards the center of the earth even though you're not moving. You still feel the attraction. And so if we were to ignore, just cover up Q2 right now with your hand for just a moment so you ignore that don't even look at this charge for right now. Just analyze the force between Q1 and Q3. What does that look like in terms of what does Q3 want to do? Well, Q3 feels attracted to the left. It feels attracted to the left because it wants to get closer to charge 1. And so the force between charge 1 and charge 3 is attractive. It's to the left because Q3 feels drawn towards the negative. Now, ignore for a second Q1. We don't care what Q1 is doing anymore. We now want to look at what is Q2 doing to Q3. And if we look at that, Q2 is pushing Q3 away. Okay, Q3 feels repelled in the other direction. And so this would be the force that is between 2 and 3. And so if I look at my sum of the forces equation, the sum of the forces between these two is going to be whatever the force is between 1 and 3 minus the force between 2 and 3. And they're minus because they're now opposing each other. Say one is attracting to the left and one is pushing to the right. And so those forces are not going to help, they're actually going to hinder each other. So let's go ahead and get it set up just like before. I'm going to pause the video and allow you some time to get that set up, and then we'll come back in a few moments and we will check to see how your setup looks and then what the final answer is. Okay, so let's check and see how we did. Hopefully you got the charges written down from earlier in the slide, but that's the charges there. So I'm going to scroll down here. Let's look at the force acting between charge 1 and charge 3. So we have K times Q1 times Q2 written in coulombs. The one tricky thing is, notice the distance. The distance is 7 centimeters or 0.07 meters. Because remember, you have to take the whole distance from Q1 to Q3. And so that's the 3 centimeters plus the 4 centimeters. So that might have been one thing that tripped you up there. But 0.07 meters is the distance, and then you square that. So if you do all of that math, you end up getting that the force acting between charge 1 and charge 3 is 23.97 newtons. And then if we do the force for charge 2 and charge 3 right in between here, plug in all your values there. It's 4 centimeters distance between, so 0.04 meters. Square that, calculate everything out. We end up getting 50.57 newtons. Now remember, these forces are opposing each other. So the force that's pulling to the left is the 23.97. And then the force pushing to the right is the 50.57. And so since they're opposing each other, we need to take the difference between the two. So my sum of the forces, or my total force, if you will, is going to be the difference between those two, and that is 26.6 newtons. Notice I have the absolute value because I just took the difference between the two numbers. I want to know what is the total force when they're fighting against each other. Now, what direction is that? Well, since the stronger force is pulling to the right, that must be the overall direction of the force. And so the overall force, the total force, is 26.6 newtons to the right. Okay, we're going to do one more problem. Now, this last problem is a two-dimensional problem, which is beyond the scope of regular physics. So if you're in regular physics, this is by no means something that is going to be on your test. However, it could always pop up as a bonus or an extra credit, but certainly it is in the scope and sequence of physics honors. And so we want to make sure we know how to do this. Now, the only thing that makes this one particularly difficult is just simply we have, like I said, two directions going. We have vertical and horizontal, which means at the very end, we're going to have to use a little bit of trig, a little bit of Pythagorean theorem to solve it, but certainly nothing that is not doable. And so let's go ahead and set the problem up. So I've gone ahead and drawn in 3 charges. We have a -1 up here. This would be Q1. We have Q2 down here. And then we have Q3 over here on the side. And what I want to do is I want to figure out what is the net force and what is the direction on Q2. So we're going to be looking at this one right here. So just like always, we need to start out with a force diagram. And so here is Q2 that is represented by that dot. Let's first figure out what is the force that is going to be experienced between Q1 and Q2. So ignoring Q3, Q2 is going to feel attracted or pulled up towards Q1, and so we end up having an arrow going up just like that. and that's going to be, like I said, the force between 1 and 2. And then over here, it's going to feel repelled to the left because this positive Q3 is going to push Q2 to the left. And so that's going to be the force between 2 and 3. So that is my force diagram right there. We'll deal with that later with the trig, but for right now, we need to figure out the value of those two. And so right at this point, I want to give you guys some practice to do that on your own. So pause the video and use Coulomb's law to figure out what's the force between charge 1 and 2, and what's the force between charge 2 and 3. Okay, so let's check our work. As I was working, I was hoping you guys spotted that it's nanocoulombs, and so hopefully you spotted that. And so when I plug in my numbers there, we have 9 times 10 to the ninth. For the first one, it's 100 times 10 to the negative ninth, not negative 6 because it's nano. And then charge 2 down here is 250 nanocoulombs. And so 250 times 10 to the negative ninth coulombs there. Distance of 10 centimeters is also 0.1 meters. Square that. All in all, the force between charge 1 and 2, or vertically, is going to be 0.0225 newtons. For the force between 2 and 3, so the horizontal right here, this is going to be, if you plug in everything correctly, 0.211 newtons. So considerably more force is experienced between the horizontal versus the vertical. But still, nonetheless, there is both components. And so what I did down here is I redrew the force diagram. So it was kind of squished up here. So I just redrew it a little bit bigger down here. And so this right here represents the force between charge 1 and 2. In other words, charge 2 feels attracted up, but charge 2 also feels repelled to the left away from charge 3. Now, if you remember vector addition, right now the vectors that are drawn are tail to tail. You cannot add them correctly if they are tail to tail. They have to be tip to tail. And so your choices are either move this vector over here, or we can move this vector up here. It really doesn't matter since I'm doing this one right now, and that's what I'm going to do. So I'm just going to move it just like that. And then what I'm going to do is I'm going to write in our values. So the horizontal force we just found was 0.211 newtons. And then the vertical component is the what was it? 0.0225. Okay, there we go. So our resultant vector is going to be the diagonal component, and that is not going to work. Sorry about that. Let me draw it in this way. There we go. That's my resultant vector. There we go. That looks a lot nicer. There's my resultant vector right there. And let me make it a different color so we can recognize that it is a resultant. I'll make it red. There we go. So the resultant vector is going to be the combination of the two, and we're going to find that using Pythagorean's theorem. And remember, the resultant vector is a mix of the other two, and so it makes sense that it's pointing a little bit up and a little bit to the left. So it's going diagonally up. And so let's go ahead and do Pythagorean theorem to figure out what that resultant vector would be. So we're going to do 0.211 squared plus 0.0225 squared. And then we're going to square root that answer. So hopefully you are proficient in Pythagorean theorem enough to be able to do that with relative ease. And I end up getting 0.212 newtons is the resultant force. And so this is going to be the total force right here. I'm going to write that down here, 0.212 newtons. And now we need a direction. So our direction, since we're dealing with triangles, our direction is actually this time going to have an angle. And so we need to figure out what this angle is right here, this theta. And so since I know all three sides, you can use whatever trig function you want. You can use sine, cosine, or tangent. I'm going to use tangent. And the reason why I'm going to use tangent is because my original values were known. I knew this one and I knew this one. This one I calculated and I rounded, so it's going to be just a little bit less accurate, but it really honestly doesn't matter. You'll get the same answer pretty much either way. But I'm going to use these two values. So according to this angle, I know my opposite and I know my adjacent because this side would be the hypotenuse right here. And so that's why it's tangent. And since I'm finding an angle, I need to use the inverse tangent. So inverse tangent, which looks like that, of my opposite, which is 0.211 newtons, over my adjacent, which is 0.0225 newtons. Make sure you are in degrees and not radians, because I know a lot of you are taking either pre-calc or calculus with this, and they do radians a lot. So if I make sure I'm in degrees and do inverse tangent of 0.211 divided by 0.0225, that's going to give me an angle of 83.9 degrees. And so if I continue on with my answer down here, it's 0.212 newtons directed 83.9 degrees. And then which direction? Now the best way to do this that I tell students is, let's see, what color do I want to do this? I'll do it in green. Is right at this point, right here, wherever your resultant is starting. So the resultant was the red. It's starting right here. At that point, draw an imaginary north, south, east, west direction. So there's north, south, there's west, and then there's east. So we can see that this angle is directed 83.9 degrees west of the north axis. And so I would say it's 83.9 degrees west of north. And so definitely, quite a bit more in depth than our previous left or right answers, but it's something that's definitely doable for sure. And so my overall answer is 0.212 newtons, 83.9 degrees west of north. Now you might be thinking in your head right now, what if I didn't draw the vectors like that? What if I did, remember how we moved the vectors? You might be saying, well, what if I did that? Well, notice your resultant would still be the same, so the 0.212 newtons would not change, but you would have ended up finding the angle right here. So you would have found this theta. And so that theta, these two angles together have to end up being 90 degrees. And so you would have ended up getting 90 minus 83.9, or in other words, you'd have gotten your angle as 6.1 newtons, or sorry, not newtons, 6.1 degrees. And then that 6.1 degrees would have been directed north of the west axis. So it would just been flipped. So I want you to just realize that it doesn't matter. You can get both of these angles are correct. 83.9 degrees west of north or 6.1 degrees north of west, they are both correct. And that concludes the video on the Coulomb's law, a little bit long, but that leaves the final video coming up next, which is electric fields.